Alright, next I want to talk about the Sinc Interpolation formula. So for this, we assume that f is a band-limited function. I.e. with bandwidth p, which means, of course, that the Fourier transform of f of s is equal to 0 for absolute value of s greater than or equal to p over 2. Okay, so since we've seen that the following, the Fourier transform of f is equal to the following product. If we take the with p, rectangle with p, and then we take the Fourier transform of f and we convolve it with Shaw's p in here. So remember that this takes the band-limited function, it periodizes it, meaning we just take this non-zero portion, we spread it out onto all the periods of length p, right? And then we hit it with the rect function here with a multiplication, meaning we just put it back to where it was, right? Which seems like kind of a pointless operation, but in fact what it does is it really kind of gives us the means for looking at the passing between time and frequency domains with this function, with this formula, tells us exactly what's going on with the function f. Okay, so we get the following from this. So first of all, we can write f of t as f inverse, Fourier transform inverse, and then f of f. So I'm taking the function f, I take the Fourier transform, then the inverse Fourier transform, I'm just back at f. Okay, now what we can do is we can take inverse Fourier transform here, and now we substitute this entire expression up here for Fourier transform of f here. Okay, so we stick that one in here, so that's going to be rected with p, and then in here Fourier transform of f convolved with Shaw's of p, and this whole function of t. Alright, so continuing, when I take inverse Fourier transform, I've got product in the frequency domain here, right? So that becomes convolution in the time domain. So we can take f inverse of the rect function, then convolve it with f inverse of Fourier transform of f, convolved with Shaw's of p, right? And then this whole thing, this entire convolution here is a function of t. Okay, so continuing on, this one then, f inverse of pi sub p, we saw that that is p sinc p of t, p sinc of p times t, sorry. We convolve that now with this is an inverse Fourier transform of a convolution now, right? So that convolution then becomes product in the time domain. So I get f inverse of f of f, right? So Fourier inverse Fourier of f, that's just f, right? So I've got in there f of t, and then I've got f inverse of the Shaw function, pi sub p. Okay, and then this is well, we can write this as a function. So now the notations are getting a little bit sloppy with respect to distributions or functions, but remember we've kind of built all that technology of working with distributions and functions. We know that we can kind of work with functions and think of them like functions with arguments and so on, but when we need a distribution, we can think of that function as being enlarged into the domain of distributions. So sometimes the tagging along of the function parameters just sort of, it just kind of goes along with the expressions like for the sinc function. We could have an expression for a sinc function, which was more like rect sub p or more like SHA sub p, but in fact, there isn't one here. If you want to put a p in there, then you just write it in the argument. It's just typically the way to do it. Okay. All right, so now we've got that product, we've got f of t there. So what happens now when we do the convolution? Let's see, I've got where am I? I'm at this line here. Right, so let's do one more here. I've got p sinc pt, right? And I've got convolution with, and then the product f of t times 1 over p SHA 1 over p. So we saw this formula before for doing the inverse Fourier transform of SHA sub p. We get this this version, and we've got a convolution now with that. Okay, so next we get that this is p times sinc of pt, and then we take the convolution of that with the following summation, right? And when I take a product of f of t times the SHA distribution, right? This is a sum or a pulse train, right? And so we get the following summation then, k equals minus infinity to infinity. And here I get the function f evaluated at k over p, right? These pulses or delta functions are spaced 1 over p apart, right? So if I'm going to take this function and multiply that function times all those delta functions, remember that even though this is a function of t, it's like I'm taking an entire function of t times each of those. Each element of the sum should be that. But the delta function in each case in the sum is only non-zero at one place, where it has a spike, right? That spike is now going to get scaled by the value of the function f at that spike value, which is going to be the 1 over p, all right? Okay, so we get that, and then we get delta. Oh, sorry, I'm gonna get rid of this p now. Yeah, I can get rid of this 1 over p, which comes out of here, out of this convolution, and then with that p in front there. So here now we just have f of k over p times delta of t minus k over p, right? So once again, this is just the SHA distribution with all those delta functions shifted over intervals of k over p for all the integers k, and it just picks up the value of the function f now at each of those. Okay, so now we've got this convolution. So how do we work this one out? Well, remember that we can, first of all, we can pull the so we can pull the sinc function into the sum, right? It's not dependent on t, so it can just go right into the sum. K equals minus infinity to infinity. Now I've got f of k over p here. And now I've got sinc of pt, and then convolve with delta t minus k over p. Now remember that if you convolve with a delta, right, that's shifted, all right, this is just going to give a shifted version of this sinc function here, all right. So we now get the summation k equals minus infinity to infinity, and we get f of k over p. And here we just get sinc function at p times t minus k over p. Okay, so we saw how that that convolution worked, right? You saw how that convolution worked before. When we get a convolution in signal processing world 4, right? This is actually an integral, this convolution here. But when you convolve with the function with delta spikes, right, what do you actually get? You're just getting the values of these functions integrating against a delta function, right? Just picks out the value of a function. But if you're doing it over an entire pulse train, right, of these all spread out by 1 over p, then you just get all those values of the function at 1 over p. It's just grabbing the values of this sinc function now at those particular places, the sinc function with the p in front of the t. Now inside of there goes exactly all these t minus k over p. Okay, and so we're basically there. We can also rewrite that, if you like, in the following way. F of t is the summation k equals minus infinity to infinity of f of t sub k, and then sinc of p times t minus t sub k. Okay, and then here where t sub k is is just k over p. These are the sample points. Right, so here's our final sinc interpolation formula. So what is this saying, basically? This is saying that if the function f is band limited with bandwidth p, right? So it's band limited bandwidth p. That's our assumption about the function f. Then what can we do? We form these sinc functions, right? Which, remember, these sinc functions look like where the main sinc function here would be at 0, and then -1, -2, -3, 1, 2, 3, 1, 2, 3, 4, etc. So essentially, this sinc function, the first one, looks like this. Now, of course, if we space it out by width 1 over p, then this would just be 0, and then 1 over p, 2 over p, 3 over p, 4 over p, etc., going in either direction. If we take translates of this one, it just means I'm translating that main peak around, right, where this has a value of 1, and then everywhere else, at all the other values of t sub k, it's equal to 0. Okay. So this is saying that I can take this function, band limited with bandwidth p, I form all these sinc functions, I can translate them all around. Now what do? I just take the function value of f at t sub k, I multiply it by the appropriate sinc function. So for instance, when t sub k is 0, right, and this is 0, this is just sinc of pt. In other words, it's just this function right here. This, of course, gives me the correct value of the function here at 0. That's sort of the obvious part of this formula. It's kind of like, well, okay, I guess it achieves the correct values at all of these t sub k points, right? Because if I put t sub k in here now for this t, right, I get this function where t sub k is in here. This is actually just the sinc of 0, right? And it's just the sinc function of 0, which is 1, and then I get f of t sub k. So clearly it works. It gives us back the correct values of f at the sample points. Okay. What have we done here? In the formula, we've just used the values of f at the sampled points times the sinc functions. But the really remarkable part of this is that what's happening here is that this formula right here is f of t, and that function here is there's just a general t in there. And that means that at any other value, let's say here, for instance, not at one of those points, at any other value, I'm getting a contribution at this value, right, in this summation. I'm getting a contribution of all the possible different shifted versions of all these sinc functions, okay? What are all those sinc functions conspiring to do is they're all adding up with all of their coefficients, all of these sampled coefficients in front. You get an infinite sum. It converges to what? It converges to this actual correct signal value, okay? So this is the idea, we're reconstructing the function f from its sample values, but when we do it with a band limited function, if we stick those sample values in front of these sinc functions, we get exactly the function f back again. That's the remarkable part of this theorem.